Statistical process control. So now we're going to learn about if a process is capable, because things can change over time. Machines can have problems, workers can get changed, have less training, have a bad day. So a process can move away from the state it was in where it was capable. So for example, if it's outputting at a certain average value, that can drift away. Its variability can increase or decrease and so on. So we want to have a way to detect when that happens. Usually when that happens, there's some cause causing that to happen that's called a special or assignable cause. And the variability caused by this cause is called assignable cause variability, or special variability, or abnormal variability. And we saw that if we go back to our slide about variation, we talked about special assignable cause variability. So whenever something is causing there to be variability, that should not be there. We want to detect that, and that's what we're going to do with statistical process control. Okay, so let's get into this topic. Statistical process control is a tool used to track a process over time and indicate if things have changed for the worse. It detects presence of special cause variation or drift of a process away from the target value. It samples the process periodically to determine whether it's in control or not. If it's not in control, then you have to investigate and check what's happening and then resolve the issue. So it kind of like rings the alarm. It's like a safety mechanism that's going to ring an alarm and notify you, or something is probably wrong with your process. You need to investigate and fix it. So we see an example of a process control chart, because charts are often used to illustrate the output of statistical process control, where you have time on the x-axis, or sample number, because samples are taken at different times. Increasing sample number shows you increasing time. So sample 1 is like time 1, sample 2 is time 2, and so on. Then you have two control limits, an upper and a lower control limit. And then you have these points connected by lines, and the points represent the value observed for that sample. So some sample statistic, maybe the mean of the sample or something like that. And if the sample statistic falls outside the control limits, then you say, oh, the process is out of control. You need to investigate that, verify that's out of control, find the problem, and then resolve it. Now, the extremely important thing, please get it in your head, say it to yourself 5 times if you have to, that control limits are not the same thing as specification limits. Remember when we talked about process capability, we had specification limits, upper spec, lower spec, and we used the specification limits to calculate process capability. Specification limits are voice of the customer. We take the customer requirements and we put them in a technical language to figure out what the specification should be. Control limits are like voice of the process. They are based on the process's statistics. Okay, so control limits are different. Control limits are, you could be within the control limits and not be satisfying the customer, because the customer doesn't care about control limits. Customer has its own specification limits. So remember, specification limits are voice of the customer. They are about process capability. They're about meeting customer requirements. Control limits are voice of the process. They are based on process statistics, and they're not the same thing. Once your process is capable, then control limits will make sure it stays capable, it doesn't drift away, or something doesn't change in it. Control limits detect presence of special cause variation, but control limits are not based on the customer. They do not tell you that you will satisfy the customer. They're two different things. So control charts use control limits, process capability use specification limits, and they are not the same thing. So don't confuse the two. Don't take spec limits to calculate your control chart, or don't take control limits to calculate process capability. Upper and lower control limits define the acceptable range of variation. And if depends on what you're plotting. So variation over the target level, whatever the statistics you're plotting, and we're going to look at what statistics we're going to we're going to study various types of control charts and what statistics to use for each. Okay, and we're going to look at what it means out of control. Okay. So when you are out of control, that's evidence that there's likely abnormal variation or special cause variation. So again, you mentioned what is the purpose of control chart? Is to detect abnormal variation or special cause variation, as it's called. So whenever you are out of the control limits, there are other ways too where you could be where they indicate special cause variation. So we'll look at that, but they will have ways to indicate to you, oh, most likely special cause variation has crept in. And one way is that the sample that you plot is out of the control limits. This is just a review of process variability. Random is a variation or natural variation in the output of a process created by countless minor factors, which is inherent in a process, depends on the equipment, the machinery, the engineering, the system of measurement, the technology you use, and so on. An assignable or special cause variation is variation whose cause can be identified. It's a special cause like equipment is not adjusted, defective materials, changes in parts or materials, poor work methods, untrained workers, things like that. And we have talked a lot about this when we talked about understanding variation. So let's look at how we're going to create these control charts. We're going to look at two types of control charts. Control charts that are based on some attribute of the product. So you take the whole product, you say, is it good or bad? Okay, yes or no type of thing. Does it pass my quality check? Does it not pass my quality check? Or which this one is about a P chart, or for a count chart, which would be counting blemishes or defects. Okay, that could be scratches on a surface. That could be number of problems or defects, number of wires not connected properly, things like that. That's a count chart, and this is a proportion chart, which deals with good, bad, yes, no type of data, and this deals with count data. They're called attribute based because you're judging the whole unit as being good or bad, or you're counting the defects in the whole unit. And then we have variable based control charts, which look at some measure, which is a number, okay, which is a number, which could have fractions to it as well. Okay, so it's not a count, it's going to be something like weight. Okay, you want the weight to be a certain amount, so what is the weight? So weight could be, 2.1 pounds, 1.7 pounds, 500 grams, 350.34 grams, right? And so it's continuous measures like that, like weight or height or a dimension or a volume or the amperes of current passing through a circuit, the voltage in a circuit, things like that. So this could be voltage. In electric things, it could be amperes. This could be height. This could be some dimension, right? This could be weight. This could be volume. Okay. This could be number of calories, because you could have 50.5 calories or whatever, right? That's not a count data, it's just the amount of something. And so when you have variable based data, then you can have a mean control chart and a range control chart, and you use both of them together. But if you have attribute based data like good, bad, yes, no, or just a count of blemishes or defects, then you use either a P chart based on good, bad, yes, no data, or a C chart, but you don't use both together. So these two are kind of independent. They use one or the other, and these two go together, the mean and the range chart. And we're going to look into more detail. So don't worry if you don't get it right now. Just remember this big picture, and then we'll get into the actual charts. Okay, so we are going to start, I believe, with this variable-based control chart, mean and range chart, okay? And you can see our data is diameters in centimeters, which is like a continuous number. Diameter of 5.02, 4.91, 4.92 in centimeters. That's the diameter of a ring that's used in manufacturing. So we produce slip ring bearings, which look like flat donuts or washers. And at an early stage in the production process of a particular slip ring bearing, the outside diameter of the bearing is measured. Okay? So we've taken 10 samples during a 10-hour period of 5 slip ring bearings. and measure the diameter of the bearings. The individual observations from each sample or subgroup are shown as follows. So you have taken 10 samples. You can see sample number K. And this is really important to know how many samples you have, because we'll need to know that. So how many samples in this table is the number of rows. So we have 10 samples. That's the number of samples. And the other thing we need to know is the sample size. Sample size is number of observations within each sample. So how many data points do I have within each sample? Well, each sample is a row. So if I look at my first row, okay, how many observations do I have in this row? 1, 2, 3, 4, 5. So my sample size n equals 5, and my number of samples is 10. Total, I have 50 numbers, right? 10 rows, 5 columns. I have 50 numbers, but I have to know the sample size. My sample size is 5, number of samples is 10. Do not confuse the two. If you said sample size was 10, you would get a different answer in your calculations that we're going to do. Okay, so make sure you understand what are the number of samples, what is the sample size. The table doesn't always have to be this way where the rows, each row is a different sample. I could flip the table and make 10 columns where each column is the sample number, and then within the column I have this 5 sample values. So just read the axis of the table. They should be labeled, and they'll tell you which axis has the sample number. So you can count along that to see how many samples you have, and then the other axis will be values within the sample. That'll give you the sample size. Also, the question text tells you take 10 samples, so 10 is the number of samples, and the 5 must be the sample size. Okay. So we're going to draw an X bar chart where X bar is the mean of each sample. And then we're going to look at a range chart where R is the range of each sample. Okay. What is X bar? X bar is just the average of a bunch of values. So if you have 5 values in a sample, you average them, you get an X bar for the sample. What is range? Range is the difference between the maximum and the minimum values. If you take a sample of 5 values, the range will be the highest value minus the lowest value. And we use both of these control charts together. We'll talk about why once we figure out how to make these control charts. So these are the formulas for a range chart. Okay, you find the range for each sample. So if you have 10 samples, so for sample 1 you'll find a range value, whatever that value is. For sample 2 you'll find a range value. Let's call it R1, R2, and so you'll have 10 range values, one for each sample. So R bar is going to be your average of these 10 range values. Okay, so sigma means add stuff up. So this sigma means add stuff up. Add what up? Add the range values. Add stuff up. Add R1 plus R2 plus R10. Add all the 10 range values because we have 10 samples. And then divide by 10 because you have 10 samples. K is the number of samples. So you get the average range for all the 10 samples. Then your upper control limit and lower control limit are going to be some constant D3 or D4 multiplied by the average range. So how do we find these constants D3 and D4? We'll look at them up in a table. So here's a table which gives us these factors A2, D3, and D4. These are the factors we need to make our control charts. So if our sample size is 5, we can see that D3 equals 0 and D4 equals 2.11. So let's do the actual calculation for our data. So this is our data given in the question with 10 samples and the sample size of 5. Okay, for each sample I find the range. So this is my R1. How did I get R1? I take the highest value. The highest value in these 5 values is 5.02. And the lowest value is 4.94. If I subtract the lowest value of 4.94 from 5.02, for this sample, the max minus the min gives me 5.02 minus 4.94, okay, which gives me 0.08. And that's going to be the range of sample 1 or R1, so I get my R1. Okay, I do the same thing for sample 2, max minus min. The max here is going to be 5.07. The min is 4.95. This gives me 0.12, the difference between them. You always take the higher value max and subtract the min, so range should never be negative. You should always get a positive range because the max minus the min. And if all numbers are the same, the max and min are the same, range can be 0. Let's say all 5 numbers were the exact same, but range cannot be negative. So you should get 0 or a higher value for range. So max minus min, this is my R2. So I find my 10 ranges, then I add all 10 up. The 1.15 is a sum of all of these values. Okay, sorry, I messed up there a little bit. Okay, so if I add up all of these 10 values, the 10 range values, the sum is 1.15. I divide by 10 because I have 10 samples, my K, and I get my average range to be 0.115. This is my R bar. So R bar equals 0.115. Let me write it here. R bar equals 0.115. I already know my D3 and D4 from here, so I have everything to calculate my upper and lower control limits. Upper control limit is D4 times R bar, or 2.11 times 0.115, which is 0.243. So that's this. And then lower control limit is D3 minus R bar. D3 is 0, so this becomes 0. So that's 0 right here. That's my lower control limit at 0. So the line at horizontal line at 0 and the horizontal line at 0.243 are my two control limits. And then within the control limits, I'm going to plot my range value. So my R1 was 0.08. Remember, if you go back here, R1, my first range is 0.08. So my first sample gives me this point. My second sample has a range value of 0.12. So I go to the graph and I plot 0.12. And then the mean, I can also plot this dotted line, which is the R bar line, which is 0.115. That's important because you want to see, the values of the samples going up and down the mean. They should vary around the mean. Okay. And so we can see that it's like a nice range chart, nice R chart, right? Where we found the upper control limit, a lower control limit, and the mean line is right here, 0.115. And then my actual range values for the 10 samples are going up and below the mean kind of randomly. That's an R chart. Okay, now for the X chart, my formulas again use the average range, R bar, which I already found was 0.115. They use a constant called A2, which I have to find in this chart. So this chart of constants will be given to you on like an exam. For the homework, you can look it up in the slides, right? So, or if it's an open notes exam, you can just go to the slides and look at this chart. So for a sample size, and this you have to go by sample size, not number of samples. If you go to row 10, it'll give you the wrong values because your sample size is 5, not 10. 10 is the number of samples, where the number of values within each sample, the sample size is 5. So you go to row 5 and A2 is 0.58. Okay, so I know A2 is 0.58. Okay. R bar is 0.15. X bar is the mean of means, and I'm going to show you how to calculate that. Basically, find X bar for each sample. You get 10 X bar values. You find the average of these 10 X bar values. You get X bar, the mean of means. And then you can calculate the upper and lower control limit using these formulas. So let's do that. So for each sample, I calculate X bar. I already have my R calculated. So now I calculate X bar. X bar is the average of these 5 values. How do you find the average? Add these 5 numbers up and divide by 5 the sample size. So all these 5 numbers added up, divide by 5, you get 4.98. Add the next 5 numbers up. Oops, sorry, I made a mistake. Add the next 5 numbers up, divide by 5, you have the mean. This value 5 is the average for sample 2. This is X bar 2 is 5, X bar 2. X bar 1 is 4.98. This is the mean of the first sample. Then your X bar 3 is 4.97. X bar 4 is 4.96. So you got 10 X bar values. So you got X bar 1, X bar 2, all the way down to X bar 10. You got 10 values right here. Okay, right here, these 10 values. Then you can sum these 5 values. That's going to give you sigma x bar, sum of all the x bar, divide by the number of samples, k, 10. So that divided by 10 will give you x bar bar will be, x bar bar will be 50.09. The sum of the 10 means divided by 10, because you have 10 samples, this will be 5.009 or 5.01. That'll be your x bar bar. Okay. So again, x bar bar is the sum of all the x bars, okay, divided by the sample, number of samples. So slight correction here. This is the sum of, this is the sum of x bars. Okay, so you had x bar 1, x bar 2, x bar 3, x bar 4, all the way to x10. Add all the x bars, divide by the number of samples k, you get x bar bar, which is 5.009 or 5.01. Okay, we know r bar from a previous calculation. We know A2 for sample size of 5 is 0.58. So we take x bar bar of 5.01. We take A2 of 0.58. We take r bar of 0.115, and we get the upper control limit by adding this, multiplying A2 by r bar, adding to x bar bar, we get 5.08. Lower control limit is a very similar formula, except you subtract. So you take x bar bar, you subtract A2 times r bar, and you get 4.94. Okay. Okay, so I fixed some errors in the picture when drawing on PowerPoint. It's not that easy. So you can see that now it looks kind of correct. My lower control limit 4.94, upper control limit 5.08, x bar bar is 5.01 right here, 5.01, that's my average. And you can see that the different samples, the x bar goes up and down, and it's within the control limit. Okay, and this is kind of like very close to the upper control limit. Okay. So that's how you can draw the x bar control chart. Okay. Now, if a point is outside the control limits, we already saw that if a point is somewhere here, you're out of control, because you've exceeded the control limits. But if you're just touching the control limits, you might still want to investigate that, because that's like really on the boundary, right? But the definition of out of control is you have to exceed the control limits. Okay, you have to be outside them. On the boundary is not technically out of control, but you still might want to investigate that. What happened? Why are you hitting the boundaries? For the mass majority of the time, you should not be hitting the boundaries. You should be within the boundaries. Okay. So we figured out how to use the formulas to calculate the control limits. Then you just draw horizontal lines at the control limits and plot your sample statistics, the x bar values or the range values on that graph. A process is in control when no sample points are outside the limits, most points are away from the limits near the process average, okay, about equal number of points are above and below the center line. So you don't just have something like this, like you're just staying above the center line continuously and you're never dropping below. It should be up and down. It should be going up sometimes, coming down sometimes, and so on. And points here randomly distributed. There are no patterns. A pattern like this, like always staying below, is like a pattern, and so this shows something fishy could be going on. Okay. Now, why do we need to use two charts, X bar and R charts, together? That's because the mean of the process might shift, or the variance in the process might increase. So if the variance in the process increases, the R chart will tell you, oh, hey, the variance is going away. And if the mean is shifting, the X bar chart will tell you, hey, the mean of the process is shifting. So they track different things. X bar chart tracks the mean, R chart tracks the variance. And for continuous data like weight, volume, like, which is like normally, where you have sample statistics which are normally distributed, in a normal distribution, the mean and variance can change independently. So you could have just the mean change, or just the variance could change, or both could change. So let's look at let's look at this example. So in the C, the picture C, where you're away from the target, that's the mean has changed, but you're still tightly clustered, variance has not changed. In picture D, nothing has changed, you're on the center and the variance is also low. In picture B, the variance has changed, but you're still around the center point. And in A, both the variance and the mean have changed because your mean is away from the center and your variance is also high. Now let's look at this example. If you look at the distribution of our data, you can see this distribution curve going up. What this means is that you had a mean value here. This was maybe your your process mean at certain time, and then at the next time period it changed. Now it's a different mean at this time, and now it's changing. It's like drifting away. You see this drift? Look at the tops of the distribution. Your process is drifting away from this value here. The gap between this value and the mean is growing. Okay, so when you have a process that's drifting away in terms of the average output it produces, this is what the X bar chart will show. It will show an increase in your points until the points go out of the control limits. So it detects the shift or the drift of the process. Okay, look at the R chart. R chart is saying everything is in control. No problem in the R chart. Why? Because the width of the distribution, the variability is not changing. Only the center of the distribution is moving. So there's a drift of the mean, but the variance is constant or the same. So R chart is saying variance is fine. Okay, variance is fine, which is true. And X bar chart is saying there's a mean drift. The mean is drifting away. Okay, so you know, looking at two charts, what's happening. Let's look at another example. Okay, here the mean is the same. No drift in the mean over time. But the fatness of the distribution is getting fatter, so that means there's more variability. So the variance is increasing over time. So look at the X bar chart. Okay, it's just merely humming along. Nothing surprising in the X bar chart. Everything is in control. Why? Because the mean is not drifting. But if you look at the R chart, it's saying, oh, variance is going up and up and up until it goes out of control. So it reveals the variance. Okay. The drift in the variance. So that's why we need to use both charts, because with continuous data like weights, volume, voltages, things like that, we model the sample statistics of them using a normal distribution. And for that, the mean or variance could change independently. Just the mean could change, or just the variance could change, or both could change, and both charts could show going out of control. Okay. Now look at control chart for attributes for our P chart. We use a P chart, and that's important to know when we use which chart. We use a P chart when each observation can be placed into just two categories, either or. It's either good or bad. It's pass or fail. You know, passes quality check or does not pass quality check. Then we take samples, okay, and in each sample, we have a sample size. So let's say we take a sample size is 5. So for each of the 5 units in a sample, we say whether a unit is defective or not defective. Okay. So if a unit is defective, it's like a 1. If a unit is not defective, that's like a 0. So let's say I took sample 1, K is 1. This is my first sample. And I got 5 pieces, 5 units of output. Okay. First unit was fine, no defect, so that's a 0. Second unit had a defect, so that's a 1. That's a defect. Third unit had a 0. Fourth unit had a defect. Fifth unit was fine, 0. So I got 3 zeros and 2 ones, so 2 defects. So instead of writing 0, 1, 0, 1, 0, people summarize it and write number of defects equals 2 for sample 1. So for each sample, they just write number of defects. Okay, but this is not number of defects for each unit. There were 2 defects in the whole sample. So this is not count data. Count data is different. In count data, you're counting defects over a surface or a time period, not examining each unit and getting 0, 1. This defect count of 2 is just a summary of my 0, 1 data. I actually have 0, 1 data. I have 3 zeros and 2 ones. That's my raw data. And the summary of the raw data is 2 defects in this whole sample. Okay, so that's going to be a P chart because each original value is a 0, 1, defect or no defect. Okay, then the formula that I use is total number of defectives divided by total number of things I examined, which is number of samples times sample size. That's my P bar. It's kind of like X bar bar for 0, 1 data. Okay, and then my standard deviation is going to be a function of P bar. So it's going to be P bar times 1 minus P bar divided by the sample size n. This will be 5 in this case, the case I just drew, because you look at 5 pieces or 5 units in each sample. And then my control chart upper and control limits are given by P bar plus Z times sigma P bar and P bar minus Z times sigma P bar. Sigma P bar comes from this formula. P bar comes from this formula. If Z is not given, just assume Z equals 3 because we draw like 3 standard deviation control charts. Otherwise, the question may say draw a P chart with a 2 standard deviation P chart. A 2 sigma P chart, 2 standard deviation P chart simply means that Z equals 2. Okay, a 3 sigma or 3 standard deviation P chart simply means that Z equals 3. And if nothing is given, then by default Z will be 3. So that's the default. Okay, so let's do an example of that. So here I have data from a bank. Okay, and we're looking at the cashier writing down some customer account number, maybe to fill a deposit slip or something. And we look at this deposit slip and we say whether the account number is correct or not, yes or no, 0 or 1. Okay, so each week we take a random sample of 2,500 deposits and we record how many of these had incorrect account numbers. Okay, so in sample 1, I had 2,500 deposits examined. Okay, 2,485 of these were zeros, no defect, and 15 of these were 1. There was a defect, the account number was written incorrectly. So instead of writing 2,485 zeros and then 15 ones, I just summarized that 0, 1 information into this 15. Okay, this is very important to understand that behind the 15 is 0, 1 data, yes, no data, that's being summarized into the 15. Okay, so don't think this is 15 is like continuous data, can be 15, that can be 10, is summarizing the 0, 1 data at the back end. Okay, and then the second week, again, I looked at 2,500 of deposits and I found that 4,988 had no problem, they were zeros, and 12 of them had a problem, they were defects, so I write the number of ones. Okay, so to do a P bar calculation, okay, you'll add up all of these defects, all of the ones for all of your samples. Okay, that'll be 15 plus 12 plus the 19 plus the 2 plus the all the way up to the plus the 3, this 3. Add up all these values. Okay, you divide that by 12 samples because you have 12 samples, 1 to 12, and each sample has 2,500 data points because the 0 ones are 2,500 zeros, 1 in each. So you divide by number of samples, K, times the sample size N. N is 2,500. Sample size N is 2,500. Okay, and that's going to give you a P bar. Okay, so let's do the calculation. So P bar is going to be 147. That comes from adding up all of these numbers. All of these and these. See, the total is 147. It's these 6 values plus these 6 values, the total of 12 values, 147. Okay, and then 12 samples and the sample size of each sample, that gives you a P bar of 0.0049. Then you have to calculate the standard deviation of P bar. That's going to be P bar times 1 minus P bar over n square root of the whole thing. That's 0.0049 times 1 minus 0.0049 divided by the sample size 2,500, then square root of the whole thing. That's going to be 0.0014. Now I can find the UCL and the LCL, the upper control limit and the lower control limit. UCL is going to be P bar from here plus Z is 3. Remember I said, see it says 3 sigma control limits. So that means Z is 3. Okay, so Z is 3, and then standard deviation of P bar is this from this calculation. I get an upper control limit, I get a lower control limit. Then I can plot the P bar of the P of each sample. How do I get the P of each sample? The P of each sample is going to be the number of defectives over the sample size n. So my P1 is 15 over 2500 over the sample size. Okay, and my P2 is going to be the 12 over the sample size over the 2500. This is like the average of sample 1, is like the average of sample 2. So this X comes from 15 divided by 2500. And this comes from the second sample, which had 12 defects over 2500. Okay, so I plot the samples and I see that sample 7 is above the upper control limit. So the process is not in statistical control. Okay, but that's what a P chart looks like. And that's how you create it using the formulas we talked about. Now it's really important to understand the count chart, the C chart, because students will often confuse the P chart with the C chart. So if you're feeling sleepy, pause the video, get coffee, walk around, wake up. This is really important. Okay, and how do we find the difference? So let's go through it and you'll see. C chart is a chart used for controlling the number of defects when more than one defect can be present in a service or a product. So remember, in P chart, it was just defective or not defective. Each unit was giving us 0 or 1. We summarized the data for the whole sample as number of defects in the whole sample, but that's summarizing the zeros and ones. Each data point was a 0 and 1. In a C chart, you don't have defective, not defective underlying data. You just look at each unit and you find how many defects it has. So for example, you look at a complex electronic circuit and you find how many wires were wired incorrectly, right? So each circuit, you can say if there's only has a number of defects. You could have 0 defects in a circuit, or 1, 2, 3, 4, 5, or a large number of defects in a circuit. So it's not 0, 1, it's 0, 1, 2, 3, 4, 5. It could be any value, 0 or higher. Okay, or you examine a piece of metal, let's say the body of a car. You go around the body of a car in a car manufacturing facility and you found any areas which was not painted properly. The paint workshop had a problem. There's a spot which is not painted properly. You count the number of spots, that's your count data. So each car is not a 0 or 1, defective or not defective. It's number of spots that are not painted properly. Could be 0 spots, 1 spot, 2 spot, 3 spot, 4 spot, 5 spot, like that. So it's not 0, 1 data, it's 0, 1, 2, 3, 4, 5, like that. Okay. Okay, and then you're going to find the average defect rate. And then you're going to use these formulas where the average plus Z times standard deviation of the average. And in this case, because it's count data, at the back end, we're using what we call the Poisson distribution. Okay. And the neat thing about the Poisson is that the standard deviation of a Poisson is just square root of the mean value. Because the mean is equals the variance basically. So the standard deviation is the square root of the mean value. So once you have the mean value, you take the square root of the mean value, you get the standard deviation of the count, and then you can use the standard deviation and the average value with plus minus Z to get the upper and lower control limit. Z is going to work just like in the P chart. Default is going to be 3, but the question might say use 3 sigma limits or 4 sigma limits or 2 sigma limits. 2 sigma limits means Z is 2, 4 sigma limits means Z is 4, 3 sigma limits means Z is 3. So let's look at an example that will really clarify the difference between count data and then the P data, the 0, 1 data. The Woodland Paper Company produces paper for newspaper industry. As a final step of the process, the paper passes through a machine that measures various product quality characteristics. when the paper production process is in control, it averages 20 defects per roll. So each roll is like a sample. And in each roll, instead of saying 0, 1, the roll is defective or not defective, you're counting the number of defects. Okay. The reason being in this example, because even a roll is so big that even with a few defects, it's going to be fine. It's still going to sell. Like, it's very hard to produce a completely defect-free roll. It's like, think about a carpet, people who like hand weave carpets. When you hand weave carpets, there could be some small defects in it, some variations, because if you're weaving it by hand. But as long as the variations are few, they're not visible to the naked eye, unless you look very closely, the carpet is still going to sell. So it's not that if there's just one defect, we throw the carpet out. It's not 0, 1, bad, good. It's how many defects there are. So you take a whole piece of carpet and you count the number of defects. That's going to be your count data. It's not going to be P-chart 0, 1 data. Same thing, we have a big paper roll, and the paper roll is not going to be perfect, but it shouldn't have too many defects. So it may have 0 defects, 1 defect, 2 defect, all the way. On average, it can have 20 defects and still be fine, right? But we want to make sure we don't start producing way more than 20 defects. So for each roll of paper, you count the number of defects. So a roll doesn't get a 0, 1 value. It's a good roll or a bad roll. Every roll gets counted how many defects there are in each roll. So you want to set up a control chart. 5 rolls had the following number of defects: 16, 21, 17, 22, 24. The 6th roll using pulp from a different supplier had 5 defects. So is the production in control? We're going to use 2 sigma control limits. Okay. So we already know that the average is 20. Okay. So we can use that because this average given in the question is a long run average. If this 20 was not given, you'd have to use this data to calculate the average. You'll calculate C bar as the average of these values. But we've already given the long run average from a lot of data. So we're just going to use that. And then we're going to plot this data to see if the process is in control or not. Okay. So we're going to use the 20. That's our C bar. Okay. If C bar is 20 from a lot of data in the past, we know our C bar, then the standard deviation of C bar is simply going to be square root of 20. Okay, and we know Z is 2 because we need 2 sigma control limits based on the question. Okay, this is 2 sigma control limits. Okay, so then we can find our upper and roll control limit. Upper control limit will be the average number of defects per roll, 20, then plus the Z of 2 times square root of 20, which is the sigma C bar, square root of 20. So we got 28.94, and then the lower control limit is going to be 20 minus Z times standard deviation, 11.06. Once we have the control limits, now we'll plot these 6 samples, these 5 and this 6 sample on this control chart. Okay, so let's plot that. So here's our upper control limit, 28.94, lower control limit 11.06. These are our 5 values from the 5 new samples we just took in the question. Okay. See, so part A, we set up the control limits using 20, and then after the control limit setup, we get this new data. So now we're going to plot the new data on those control limits, 16, 21, 17, 22, 24. Okay, so we plot that 16, 21, and so on. And then the last value was 5. So this is out of control. Okay. The process technically out of control because we got too few defects. Okay. But remember, this was pulp from a different supplier, new supplier. So it's possible that the new supplier's pulp enables us to work at a better level than we were working before. So it is out of control, but in a good way. We still want to investigate that. Is it a one-off thing? Maybe you just got a batch of really good pulp, or is the new supplier always giving you such high quality pulp that you're going to have lower defects, and then you can switch to the new supplier and remake your control limits, and so your new control limits might be a lower limit of 2 and an upper limit of 10 or something, and then you have defects around 5 between that. So you may go to a new control charts and a new level of performance of the process if this can be maintained. It's not a one-off thing. So you still investigated at special cost. Something changed. It gave you a good output. You don't want defects, but something did change this special cause. You investigate it. And if the new supplier's pulp is really that much better, then you can switch to the new supplier and then recalibrate your control charts. Okay. So hint about C charts. C charts are going to be counting number of defects, either a unit of time. So it could be, okay, how many accidents happen in a factory in a month or on a road in a month. So it could be over a unit of time, the number of accidents that happen. That could be a C chart. It could be over a unit of space. Okay. That could be like a roll of paper, a sheet of metal, how many defects, a windshield of a car, how many defects on it, right? So it could be unit of space. So usually you're counting defects on a unit of space or time. That's a C chart. P chart is when you are taking each unit to be a 0, 1, good or bad. And because in a sample you look at many units, you summarize the sample as number of bad units in a sample. That's number of defective units in a sample. Okay, but number of defective units in a sample is different from number of defects on a unit of time or space. So they're different things. Okay, so if the underlying data is 0, 1, yes or no, and then you're summarizing a sample by number of bad units in a sample, that's a P chart. But if the underlying data is not 0, 1, you're just counting defects on a unit of time or a unit of space, like a sheet, a roll of paper, or a unit of time, actions in a month, then you're going to go with a C chart. Okay. Now, the statistical process view of quality. Quality is inversely proportional to variability in a process. And quality improvement is the reduction of variability in a process and outputs. So you want to control, and also you should probably add the average output of the process. Because if the average output is way off target, that can also create quality problems. Like here, this is our target in the middle, and our average is way off target. So you could be off target by mean drift, right? Or you could be off, or you could have a very high variability like here. And this is good. This is your mean. You don't have mean drift and you have low variance. So mean is on target, and low variability around the mean. This means we're doing good in terms of quality. Okay, that's a SPC view. And if the mean moves away or the variance moves away, then we can have defects. There's some special cause relation likely present that's causing the mean to drift or the variance to go up, and we investigate the special cause variance. Now you might wonder, when we did the X bar and R chart, the first example, right here, we use two charts, right? X bar chart and a P chart. And then when we go for attribute data, like P charts, we only have one chart. Look at that, just one chart. Why? Because if the mean changes, the mean in this case is P bar, then the variance automatically changes, because the sigma P bar is a function of P bar. If P bar changes, this will change. Whereas for the normal distribution, that's not the case. The mean can change independently of the variance. And so when you have the normal distribution in the back end driving your control chart, you have to have two charts, one for the mean, one for the variance. But when you're using a different distribution for a P-bar data, this is a binomial distribution. In that, the mean and variance are related. If one changes, the other changes. You can't just change the mean, it'll change the variance. So if you're out of control on the mean, you're out of control on the variance, and vice versa. So you just need one control chart. Same thing with count data. When you go to a C chart, like right here, you only need one chart, because look, the variance and the mean are related. If this 20 changes, the variance changes. If the variance square root of 20 changes, this 20 changes. They're driven by the same phenomena. Like if the mean goes up, the variance goes up, the mean goes down, the variance goes down. So because they move in tandem, if the mean is out of control, the variance is out of control, and vice versa. Okay, so you only need one control chart. Okay. So now let's look at some other ways, some ways we can be out of control. So let's look at this control chart, and we can see that there's no pattern, there's no distinct pattern, and there's no value outside the control limits. Okay, so we are good. In control process, no action needed. Now let's look at here. There's no value outside the control limits, no value outside, because this is my upper control limit right here, UCL. This is my LCL. Nothing else outside. But there is a pattern. What's the pattern? We have a long run of values below the mean. And this is a red flag. Why? Because on average, you're going to be probability 50% chance you're going to be below the mean, below this is the X bar or P bar, the long run average value of the process. Okay, so below the mean value, okay, and there's a 50% chance you're going to be above the mean value, because that's from the definition of the mean. For symmetric distributions, you're going to be half the time above the mean, half the time below the mean. So the probability of being below the mean is a half. So the probability of observing this point below the mean is a half. Then probability that this point is also below the mean, this is a half. So the probability of observing 2 points consecutively below the mean is a half multiplied by a half, or 1/4. Now we have a third point consecutively below the mean. So what's the probability that we get 3 points consecutively below the mean? That's going to be a half times a half times a half. That's 1/8. Pretty small number. Oh, what about 4 points? That's going to be 4 consecutive points below the mean. It's going to be a half to the power 4. 5 points, a half to the power 32. And you can see this is getting very, very small. A half to the power 64, a half to the power 128. That's getting like really low probability. So you see 5, 6, 7 values in a sequence below the mean. Something is happening. Something happened here. So this is not in control because of the pattern. A long below mean run means there's probably some special cause acting. You should not get such a long pattern below the mean, because it's very low probability this could happen if things were happening normally. And so you need to investigate. Okay, so there's a pattern, so it's not in control. Here you have a value outside, another value outside, so you're obviously not in control, right? You're exceeding the upper limit than the lower limit, so special cause is likely present. Okay, so that's how we will look at control charts. That's how they indicate to us that there's special cause variation present. Remember we said control charts are like an alarm, which tells whether special cause variation is present. The alarm goes off if you're outside either of the upper or lower control limit, or you have a distinct pattern. Okay, and there are actually formulas to detect patterns, and so there are actually formulas where you can count different things and put them in a formula, and it'll give you like a value. You can compare with a threshold value or something like that and see is there really a pattern here or not. And so a bunch of values very close to a control limit is also cause for concern. Let's say let's say you got a value. Let me show you here. Let's say the next value was right here, then another value was right here, another value was right here. Just 3 values very, very close to the upper limit. That's also like suspicious. That shouldn't really happen, because it's further away from the mean you are, the more unlikely it is to be far from the mean. You got 3 values in a row that are far from the mean. They're really on the upper control limit. So that might be cause for concern as well. Okay. Okay. Now, remember we said that we use z equals 3 for our control charts. Usually the default, and we could use another value. So control charts are not perfect. They're probabilistic. So there is a chance they can be wrong. The type of errors we can make when we look at a control chart and take a decision are 2 types. Type 1 error is a false positive. What is a false positive? Okay, so a false positive is, let's say we observe this. Let me just remove the ink. So we saw this, we go investigate for special cause. There is a small chance that there was no special cause, because there's a tiny probability that you can be outside the control limit with just normal cause variation present. Because remember, the control limits are like 3 sigma limits. So with 3 sigma limits, there's a tiny probability, like less than 1%, that you can be outside the control limits without there being a special cause variation. Okay, it's like hypothesis testing. When you reject the null hypothesis, there is a chance you could be wrong. There is a chance that null was true, but you have a false positive. You rejected null incorrectly. It's kind of like that idea. So there's a tiny chance, a small chance that that the control chart says out of control, but actually nothing happened. It's just random variation. So if you conclude looking at the control chart, or the control chart tells us there's special cause variation, but there really is not. It's just normal variation. It's just a freak type of, it's just like an unlikely event that happened. Then that's called a type 1 error. Okay, that's a false positive because the controller said, hey, we're out of control, but we're actually not out of control. The other type of error is a false negative. What could happen is control chart could say, oh, everything is fine and dandy, but there's actually special cause variation present. The special cause variation is small right now, so maybe it's not that easily detectable by the control chart. And if it grows, it might become detectable. But there is a chance that there's some special cause variation present and the control chart is not detecting it. That's type 2 error. Okay. So this table illustrates this very nicely. Okay. So if the process is actually, the reality is in control and the control chart agrees with the reality, we are fine. Because that's the truth. Like our output agrees with the reality. Or if the process is actually out of control in reality, this is your reality up here, in reality, okay, and the control chart says we are out of control, so it matches the reality, then again we are okay. I mean, we are not okay that we have to investigate the special cause and fix it, but we are okay that our control chart is telling the truth. It's matching the reality. But if the control chart says out of control, and it's actually in control, that's a false positive, that's a type 1 error, false positive. Or the control chart says we're in control, but reality is we're out of control, that's a false negative. Because control chart said negative, no problem, but there is a problem, false negative, that's a type 2 error. Okay. So when you set your control limits, you're picking a trade-off between type 1 and type 2 error. 3 sigma control limits are going to reduce type 1 error because the limits are wide. There's a very small chance you're going to have a false positive. If you have 3 sigma limits and the control chart says something is up, almost always something will be up. There's a very tiny chance of a false positive because only 0.27% chance of an out of limit observation being due to common cause variation. However, the risk of type 2 error may be more because your limits are wide, so something could go wrong and you don't immediately detect it. You will eventually detect it if it keeps going off and off and off. You'll eventually go outside the control limits, but you'll not detect it immediately, so you'll have type 2 error for some time. Now, if we make the control chart limits narrower, like 2 sigma limits are narrower together, then you reduce the risk of type 2 error. False negatives go down. If there's something goes wrong, you quickly detect it because it quickly goes out of the narrow control limits. But you increase that risk of type 1 error, you get more false positives because about 5% of the time when you get an out of control signal from the control chart, actually nothing would be wrong. It'll just be normal variation, and 5% of the time you're going to get a false positive if you use 2 sigma limits. So what should you do? Should you use 2 sigma limits, 3 sigma limits, 4 sigma limits? It depends on the cost of each type of error. What does a type 1 error cost you? What does a type 2 error cost you? Type 1 error means a false positive. So you go investigate and you find nothing is wrong. What is the cost of this investigation? If you have to stop an expensive process to investigate and the cost is very high, you don't want to stop the process needlessly. Okay? So we prefer wider control limits if the cost of stopping the process and investigating special cause is high, because you don't want type 1 errors because you'll be just stopping it for no reason and just wasting production time. Okay. Also, highly capable processes have a large margin to shift by before they will produce out of spec products. Okay. So if control limit is set at 3 sigma, type 2 error is not as expensive because type 2 error says there's starting to be some drift for some special cause. But for a 6 sigma process, you could have a lot of drift and still be not producing defects. So we can allow for some type 2 error and kind of wait for the type 2 error to get extreme, like an extreme drift away from the mean until we detect it, because if you have a highly capable process, the cost of type 2 error is low. However, if we have a process where a small drift causes a lot of cost for us, it causes huge defects, then you want narrower and stopping and investigating doesn't cost much. Maybe you can investigate without stopping the process, or you have some diagnostics data being collected by automated sensors. You can look at that. And so there's almost no cost to investigating. Then you might go for narrower control limits, because type 1 error has no cost. There's no cost to investigate, but type 2 error has a cost because your process is not Six Sigma capable, and any small drift starts causing defective output. Then you can have like 2 sigma control limits. So you trade off the type 1 and type 2 error based on the cost of each error to determine your control limits. And that is it for statistical process control. To summarize, statistical process control, its main purpose is to raise a red flag whenever it feels it's going to be special cause variation. Hey there, look at me, I think there's special cause variation. Okay, and when it raises the red flag, there could be a false positive, and when it doesn't raise the red flag, there could be a false negative. There could still be something going on. The cost of the type 1 and type 2 error determines where you set the control limits, because if you set them wide, type 1 error will happen less frequently, but type 2 error could happen for a time before the process goes so out of control that you detect it. You're not going to detect it immediately, but there's going to be less false positives. If you set the control limits narrower, there's going to be more false positives, but you'll detect any change in the drift or the variance of the process very quickly. And our control charts are basically 3 types. The first is X bar and R chart used together when you have continuous variable data like weight, voltage, amperes, dimension, length, width, diameter. Then you have a P chart when you have 0, 1 underlying data. You take a sample and each unit in the sample gets a 0 or 1, yes, no, defective, not defective. Then you summarize the sample by saying how many units were defective in the sample. Or you have count data, which is you count the number of blemishes or defects over a unit of time, like how many accidents per month, or over a unit of space, like how many defects on a roll of paper, and then you have count data. Okay, and so that's a summary of statistical process control. If you have any questions, you can reach out to me.